All right, looking at solution equilibria, this will be part 3. This is just another buffer calculation example. So I'm going to work through two kind of different situations, and the reality is with all this, it's just you need a lot of practice doing a lot of different situations, and then you sort of get to understand the chemistry, because this is really about understanding the chemistry, and knowing the math is helpful. But if you don't know what's going to happen or have any idea how to predict what's going to happen, you just can't go anywhere with the math. So here's a situation. What if I was to take and put this is sodium acetate with nitric acid. Well, what do we have here? We have a weak base, right? We can tell that that's a weak base because sodium's not going to do anything. And when the acetate ion goes into solution, it's going to do this. It's going to pick up hydrogens from the water and create acetic acid and leave some hydroxide ions. So this is a weak base. And we can sort of figure that out from looking at it. And nitric acid is one of those strong acids that we've memorized. And so this, of course, goes into water. It's complete reaction. So we have an arrow here. It's not equilibrium. It completely dissociates. All right, so the situation would be, could we create a buffer with these two things, and how would we do that? So if you were to take this weak base and this strong acid, if you were to add a little bit of this strong acid, here's what would happen. When you add this HNO3 in there, instead of the water taking the hydrogen, well, now this acetate ion can take the hydrogen, right, and become this. And so then you won't end up with these hydroxide ions. It'll look more like this right here. Here's the net ionic equation for what's going to occur. Now you couldn't do too much. I mean, if you put too much of this nitric acid in there, it's just gonna totally dissociate. You're gonna end up with a ton of extra ones of these, and it won't be any sort of a buffer situation. It'll just be a very, very acidic situation, right? So what you do is you add just a little bit of it, and so some of those hydrogens ends up going with some of the acetic acid or the acetates and creating some of this acetic acid, and then the rest of the acetate ions will still be in there. So then what you have is you have a conjugate acid-base pair in excess. Or sort of both kind of existing in there. And so now if I add some acid, well, it's going to be sucked up by this. And if I add some base, it's going to be sucked up by this, and it's going to go that way. So that's how the buffer works. So let's look at one more situation. What if we are to take 1 liter of a strong acid? So we're going to take 1 liter of hydrochloric acid, and we're going to take 1 or 2 liters of this strong base. Okay, so we know that that these are going to completely dissociate, and clearly whichever one has more moles is going to determine the pH of it, right? So if I end up with more moles of this, I'll end up with more moles of hydrogen, therefore it'll be acidic. If I have more moles of this, I'll end up with more moles of hydroxide, and therefore it'll be basic. But so we have a 1 liter 0.1 molar and a 2 liter 0.06. It's not readily apparent, but if you look at it long enough, you can figure out that this is going to have slightly more. I went ahead and did some of these calculations for you. So when we put these things together, of course, they neutralize. So when we have the hydrochloric acid and the sodium hydroxide, we put them together and they create water, right? And so then here's the net ionic equation. So the net ionic equation is going to show us that we have just the hydrogen here and the hydroxide here. And of course, the characteristic of strong acids and bases, oops, I did the wrong one. The characteristics of strong acids and bases is that they have these spectator ions, these neutral ions that really don't do anything. And so this right here It just stays dissociated and does not get involved in the acid-base thing at all. So then, of course, we still have to get to our question of, is this going to end up acidic or is it going to end up basic? Well, the simple answer with a strong base and a strong acid is which one has more moles. So then just go about finding that. So the moles of hydrogen are going to equal the moles of HCl. So how many moles of HCl? Well, we have 1 liter, and it's 0.1 molar. So we have exactly 0.1 moles. What about the moles of hydroxide? Because the moles of hydroxide are going to equal the moles of sodium hydroxide, right? So let's go ahead and do that. So then we have 0.060, and we have 2 liters of it. And remember the 0.060 number, the 0.060 is the amount of moles per 1 liter, because that's what equals molarity, right? So the molarity here is per 1 liter. So if I have 2 liters of this, I'm going to double that amount of moles. So I have 0.12 moles. Well, there you go. Here's the difference, 0.1 mole versus 0.12. So my difference is exactly 0.02 moles, and I have an excess of hydroxide ions. So what do we know so far? Well, we know this is going to be basic, obviously, because we have an excess of hydroxide ions. So now what we have to do is we have to figure out, well, what is the molarity of those hydroxide ions? We have a new amount of volume because we no longer just have 2 liters and no longer just have 1 liter. We've put 2 plus 1, and that's going to equal 3 liters right there, right? So we have exactly 0.2 moles excess hydroxide, all the rest of them turned into water. 0.02 moles excess hydroxide divided by 3 is going to give us 0.67 molarity. So that's our OH. So now to turn that into pH, of course, we do what we've always done. We take the logarithm of that. So the negative log of that number is going to give us 2.108. So 2.108 is going to be our pOH. Now, always keep in mind whether or not you are taking the negative log of a hydroxide ion concentration or whether it's a hydrogen ion concentration. So pH, of course, is hydrogen ion concentration. And if you're doing OH, you're going to be looking at a hydroxide ion concentration. Easy enough to convert, though, because pH is just 14 minus the pOH. So we know the pOH is 2.18. So if I take 14, subtract 2.18 from it, I get 11.82. So the pH of my solution is 11.82. Does that make sense? Absolutely. We figured out that we're going to have an excess of sodium hydroxide, so we know it's going to be basic. A number like 11.82 tells us that it indeed is basic.